Hi there. Okay, so we just have one little bit more to cover in our Chapter 3 material. So, recall from last time what we were doing was we were graphing systems of linear inequalities, and then what we wanted to do is find what the feasible region was and the corner points were. Okay, I am going to come back and do a few more examples, but before I do that, I'm going to motivate why we're doing this by going through setting up some word problems with you. Okay, so one word problem that I will do is the following. And I will guide us again through every step of the way. So I am doing in section 3.3, this is number 33. Okay, as always, I'll write down all of the relevant information. So this says that a division of the Winston Furniture Company manufactures dining tables and chairs. Okay, each table requires 40 board feet of wood and 3 labor hours. So this is wood and this is labor hours. Okay? And each chair requires 16 board feet of wood and 4 labor hours per chair. The next thing that we're given is the profit for each table. So I'll put profit right here, is $45, and the profit for each chair is $20. In a certain week, the company has 3,200 board feet of wood available and 520 labor hours available. And then what they ask is how many tables and chairs, so I'll just write how many of each should be produced to maximize profit. Okay, so I always write out my word problems in a certain way, the directions and the steps, because even if these aren't explicitly written out, this is the way you should always approach a word problem. Okay, part A is always to define your variables. In a word problem, you're always looking for something, and it's important to define that right at the beginning. So, if you're curious on how to define your variables, the way to do it is go to the question that is being asked. So, how many of each should be produced? There's my question. So, I'll let X represent the number of tables, and I'll let Y represent the number of chairs. Again, it is not sufficient to just say X is tables and Y is chairs, because we're looking for a quantity and you need to indicate that. All right, part B, I'm going to ask us to do 2 things. The first thing we're going to do is state our objective, and then the next thing that we'll do is give our objective function. Okay? In other words, when we state our objective, what's the goal here? Well, the goal is to maximize profit. Whenever you're stating your objective, it's going to be 2 words long, and essentially it's either going to be maximize something or minimize something. Okay? So, to state the objective, you really just need to continue reading the problem. So, the objective in this case is to maximize profit. Well, if that's our objective, then our objective function is going to involve profit. We usually call our objective function Z. So let's talk about the profit that we're going to get. Okay, well, how much profit do we get per table? $45. So, will you grant me that the total amount of profit I'm going to get from my tables is $45 per table times the number of tables? Plus, well, the profit per chair is $20. So isn't the total amount of profit that I'm going to get from my chairs 20Y, $20 per chair, times the number of chairs? Okay, now the last part is to give the constraints. Obviously, we're limited by certain things. Yes, we want to maximize our profit, so in an ideal world, we would have people working endlessly and we would have an endless amount of wood with which to make these things. But we're constrained by certain things, okay? So whenever I ask you what your constraints are, what I want to know is what are the limitations? Well, I claim that there's two limitations going on here. One limitation is the amount of wood we have. Do you agree that the amount of wood that I can use is less than or equal to 3,200 feet? Yes. All right. Well, let's talk about how much wood we use per item. We use 40 feet per table. So isn't the amount of wood that we're going to use for our tables 40 feet per table times the number of tables? Plus, well, how much wood do we use for our chairs? 16 feet per chair times the number of chairs. So this is one of our constraints. Now the other constraint involves the number of labor hours available. They have a maximum of 520. So the amount of labor hours we can use for that week has to be less than or equal to 520. Well, the total amount of labor hours for our tables is $3 per 3 hours per table, excuse me. So the total amount for tables will be 3x. And the total amount for our chairs will be plus 4y. All right, now there's one more that we put. You always want to put this just by default, that x and y have got to be greater than or equal to 0. Okay? You can never have a negative number of chairs or tables that you're going to be making. All right, so we have now set up our word problem. Now, this might look very similar to the systems of linear inequalities that we were solving before, and that's because that's exactly why we would solve these linear inequalities. Okay? So, this is one example of setting up a word problem. I will tell you that on an exam, I won't actually ask you to solve the word problem that you set up, for the very reason that perhaps you made a little mistake setting up a word problem, okay? Then you might be trying to solve a system that's not even solvable. So what I like to do is split up your test questions into two separate questions. One of them is, given a word problem, can you set up your system? Okay? And then another question is, given a system, can you actually go through and solve it? So I will be splitting these up. All right, let's go through one more setting up of a word problem. Well, these will still be the same, but our story is going to be a little different. Okay, so I'm going to take one similar to one in your book, but not exactly one in your book. Let's see. All right. Actually, let's do 39 in your book. Minimizing mining costs. Perth Mining Company operates 2 mines for the purpose of extracting gold and silver. So we have what's called our saddle mine And that costs $14,000 per day to operate. And it yields 50 ounces of gold and 3,000 ounces of silver per day. And then we have our horseshoe mine. Now those costs are $16,000 per day to operate. And here, 50 ounces. Here we're going to extract 75 ounces of gold and 1,000 ounces of silver. So it says that company management has set a target that they want at least 650 ounces of gold and at least 18,000 ounces of silver. And what we want to know is, well, I'm going to change this a little bit. Let's see. Okay, here we go. How many days should each mine be operated so that the target can be met at a minimum cost? Okay, so again, to define our variables, you go to the question that is being asked. How many days should each mine be operated? So why don't we let X be the number of days for our saddle mine, and we'll let Y represent the number of days for our horseshoe mine. It would help if I could spell, so horseshoe. Okay, next we want to state our objective and give our objective function. Well, isn't our objective to minimize our costs? Remember, your objective is always just 2 words long. So if our objective is to minimize our costs, that means our objective function is going to be our cost function. So how much does it cost per day to run the saddle mine? $14,000. So isn't the total cost 14,000x, right? 14,000 per day times the number of days. And for our horseshoe mine, it's $16,000 per day times the number of days. All right. Now, we're constrained. Obviously, the cheapest way to run things is not to even open them up. However, we need at least 650 ounces of gold and at least 18,000 ounces of silver. So, let's talk about this. How much gold do I get per day? Well, I get 50 ounces of gold per day from my saddle mine, so isn't that 50x? 50 ounces per day times the number of days. And how much gold do I get from my horseshoe mine? 75 ounces, so plus 75y. Now, I want at least 650 ounces, so doesn't that have to be greater than or equal to 650? All right, now let's talk about silver. From my saddle mine, I get 3,000 ounces of silver per day. times the number of days. And with my horseshoe mind, I get plus 1,000y. And in this case, we want at least 18,000 ounces of silver. All right, my last constraint is that x and y both must be greater than or equal to 0. All right, so here's a couple examples of the word problems. Now, notice, essentially what we have with these word problems is we're wanting to maximize or minimize something subject to constraints. Okay? Now, let me show you then how we would go through and actually solve this. So, let me show you a much nicer, simpler example to graph. Suppose I wanted to, say, minimize z equals x plus 3y subject to these constraints. How about x plus 2y is less than or equal to 8, x plus y is greater than or equal to 4, x is less than or equal to 2, and x and y are greater than or equal to 0. Okay? So this should look somewhat similar to what we've been setting up. But again, I will give you a system that can actually be solved. All right? So these are my constraints, and this is what I want to minimize in this case. Okay? Now, the way you do these is the following. I'm going to write out your steps, and this is what you do for all of them, and then we'll actually go through and graph this. Okay? The first step is to graph your system of inequalities. You ignore this until the very end. Okay? After you graph the system of inequalities, the next thing you do is you find your corner points for the feasible region. Remember, the feasible region is the region that satisfies all of your inequalities at the same time. So first you graph these inequalities, then you find your corner points, and then you test your corner points into your objective function. I'll let you read the details in your book, because your book does give a very nice explanation as to why the corner points are the ones that work. But it turns out that when you have a system of linear inequalities, the only values that can maximize or minimize something are your corner points. Okay? Now, when I graph things freehand, it's not as obvious what my corner points are. All right? But I assure you, on your tests, you will have graph paper, and assuming that you bring a straight edge with you, you will be able to look and see exactly what your corner points are. They're going to be at really nice numbers. Okay? Now, one quick comment. This last guy you should always be excited about. Remember, that just tells you that you're in your first quadrant. Okay? So, let's go through and graph these guys. So, you may or may not recall, but you're about to, that I always like to graph these using intercepts. If you want to solve each of them for y and use your slope and y-intercept, go for it. I like to do my intercepts. So, for example, if I set x equal to 0, that nixes my first term. Aren't I solving 2y equals 8, therefore y is 4? And in a similar manner, if I set y equal to 0, well, that nixes this term, and I just get x equals 8. So, for this line, which I'll do in green, I have y is 4, and 2, 3, 4, 5, 6, 7, 8, and x is 8. Play connect the dots. And there we have our line. Now we're not quite done because recall I need to shade. The way we determine which side to shade on is we take a test point. Okay? And if when you plug your test point in, you get a true statement, you shade on the side where that test point lives. If when you plug in your test point, you get a false statement, you shade on the other side. So if I test 0, 0 in here, well, plugging 0, 0 in here, I get 0, and I'd get the statement 0 is less than or equal to 8. I think you'll grant me that's a true statement. So since 0, 0 lives on this side of this line, that's this side I would shade on. And there's my first line. My next line, I'll again find my intercepts. This is a great situation, right? Because if I set x equal to 0, isn't y 4? And similarly, if I set y equal to 0, that will give me x is 4. So here's 4, and there's 4, and there I go. Okay, again, I need to know which side of my line to shade on. I'll take a test point. If I plug 0, 0 in here, I get 0 is greater than or equal to 4. Is that a true statement? No, that's not a true statement. So since I tested 0, 0, and I got a false statement that says I shade on the other side of my line. So I claim at this point my feasible region, in other words, the region that satisfies both of these guys, is right in here in my triangle. But I got another line here. I have x is less than or equal to 2. Okay, so what am I going to have? Well, what does the line x equals 2 look like? Isn't that a vertical line? And since I'm interested in it being less than or equal to 2, I'm going to shade to my left, and this here is my feasible region. Okay? Now this xy greater than or equal to 0 just tells me that I'm living in my first quadrant, which is exactly what I have there. So I have done step 1. That's the hardest step. Okay? The next step is to find my corner points. So in other words, we want to find these points that are on the corner of my feasible region. Now, even with this graph that I did totally freestyle, I can read my corner points. All right? Here's one corner point. That's my y-intercept. That's 0, 4. This corner point looks to be 2, 2. Okay? I know my x value's got to be 2 because it lies on the line x equals 2. Well, let's see if that actually is the case. Well, look at how it meets my red line, and I think you'll all agree if x is 2, y must be 2, otherwise we're not going to get 2 plus 2 equals 4. So I have this pair 2, 2. Now this looks like it's at 2, 3. Again, you can always verify it because I know x is equal to 2. So if I plugged in x equals 2 and y equals 3, I have 2 plus 6, and yes, in fact, that is 8. All right, so now I found my corner points. Last but not least, now is when you take your objective function. And what you do is you plug in your x, y values for each of your corner points into the objective function. So if I plug in x equals 0 and y is 4, I have 0 plus 3 times 4, which is 12. if I plug in x equals 2 and y equals 2, I have 2 plus 3 times 2, which is 8. And here, if I plug in 2, 3, I have 2 plus 3 times 3, which is going to give me 11. All right. Now, did we want to maximize or minimize? I claim we wanted to minimize in this case. So I ask myself, which is my smallest value here? I think you'll agree that it's 8. So what I would say is that my minimum is 8. And in case you're interested, it occurs when x is 2 and y is 2. Pretty cute, huh? All right, how about we go through one more example of this? So, how about this guy? Let's take, doesn't matter whether we choose to maximize or minimize. Let's maximize. How about z equals negative 2x plus 4y subject to. Okay, how about 4x minus 5y is greater than or equal to 20. X plus y is less than or equal to 14. And x and y are greater than or equal to 0. All right. Again, my first goal is to graph my system. So let's do it. I'm going to do my first line in blue. So if I set x equal to 0 here, would you agree I'm solving negative 5y is 20, and therefore y is negative 4? So I'm at negative 4. And if I set y equal to 0, well, that gets rid of this term. I'm solving for x is 20, so then x is equal to 5. All right, play connect the dots. And there we go. We can test a point now. Again, I'll test 0, 0. If I plug in x equals 0 and y equals 0, I get a 0 here. And I get 0 is greater than or equal to 20. Is that a true statement? No. So, since 0, 0 lives on this side of the line, I'm wanting to shade on the other side. So I'm shading over here. All right. My next line is x plus y is less than or equal to 14. This is a pretty nice one because if x is 0, we know y is 14. And if y is 0, x is 14. Okay, so we got to go over to 14 now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh boy, this is not going to be a very straight line, but I'll do the best I can. There we go. All right, now we need to take a test point again. So, how about 0, 0? What an original idea, huh? Okay, So if I test 0, 0 in here, I get 0 is less than or equal to 14. And what are you all thinking? Of course it is. So since 0, 0 lies on this side of my line, and I got a true statement, I'll shade on this side of my line. All right then. Well, this last guy tells us, hey, stay in your first quadrant. So we will. I claim then that gives us this as our feasible region. Okay, next thing, corner points, okay? Two of my corner points are pretty clear because they're both x-intercepts. All right, so this corner point is the x-intercept of my top line, which we found to be 5, 0. This x-intercept is the x-intercept for my red line, which we found to be 14, 0. So the only corner point that might give us some trouble, especially given my graph, is this guy. Okay? Isn't this where red line meets blue line? Yes. Now, let me make a quick comment. On the test, you will have graph paper and you will see exactly where these lines meet. Okay? I can't even begin to guess where my lines meet. I know it's some x value between 5 and 14, but I drew a pretty crummy little graph. So, let me just back up for a second and relate this to something that we've done. Aren't we looking where 4x minus 5y equals 20 intersects the line x plus y equals 14? Okay, we're looking for the ordered pair that lies on both of these lines. And I claim we know how to solve something like this because this is a system that we've solved using substitution or the addition elimination method. So I'm going to just real quick write my objective function here. We want to maximize him. So just for practice purposes, let's go through and solve this system. Okay? Again, you won't need to do this in this problem, but it's really good practice to know how to solve systems. So we could say, which variable should we get rid of? And I'm going to get rid of my y's because I already have a negative here. So since I have a negative 5y here, if I had a positive 5y, I'd add these guys up and my y's would go away. So I'm going to multiply my bottom equation by 5. So my top equation is 4x minus 5y equals 20. My bottom equation is 5x plus 5y is 70. Add them up. What is 4x plus 5x? 9x. My y's cancel, and I get 90. So, x is 10. 6, 7, 8, 9, 10. Actually, that's not even that bad. Okay, now I have my x value. I need to find my corresponding y value. I would take that and plug it in this guy, right? Because if x is 10, 10 plus what is 14? 4. So there are my 3 corner points. All right. Next, we just go and we plug them into our objective function. So if I plug 5, 0 in, don't I have negative 2 times 5 plus 4 times 0, which is negative 10? For this next guy, I have negative 2 times 14 plus 4 times 0. So I'm going to get negative 28. And last but not least, I'll plug in 10, 4, and I get negative 2 times 10 plus 4 times 4. Well, here I have negative 20 plus 16 is negative 4. All right. Well, we wanted to maximize this guy. Which is my largest value? -4. So what we would say is that our maximum is -4. And in this case, it occurs when x is equal to 10 and y is equal to 4. All right, that completes our lesson. Thank you.